Dr. Webster is a professor in environmental health at Boston University School of Public Health. And he's also a San Diego local, I think, or at least he spent a good amount of time here in San Diego. And so he's been here, and now I think you are back in Boston, and then later on, I think in this year, you'll be coming back. So
I'm actually here in San Diego today.
Oh, you are today. Fantastic, Tom. Well, it could have been done in person, but
yeah, I got here last night. So
oh, well, fantastic. Well, you will have to connect as well while you're staying, Tom. And so he's been doing a good amount of work, and he has two main areas of research. One of his is trying to understand the effect of multiple exposures or mixtures of exposures and how that affects health. And that's what the talk that we'll be hearing about today is about. So this is mainly with the idea that we're exposed to a lot of different chemicals in our day-to-day lives, whether from the environment, from our own behaviors, such as smoking, to diet, and even medications. Then, as you can imagine, all of these different chemicals may be interacting with one another, and how these may be affecting health is actually a very, very complex way to analyze this. So we'll be hearing about some of the work that he's doing on that. But he's also doing a very comprehensive analyses of forever chemicals, specifically what are called perfluoroalkyl substances, PFAS. And these are chemicals that are now present just about everywhere, thanks to their water repellency properties, to fat repellent properties. And so these were introduced into our homes through nonstick cookware, Teflon, and also, of course, they're used in anything that has to do with water repellency, water repellent clothing, and such. Dr. Webster has served as president of the Society of Toxicology Mixtures Specialty Session, and also he served in different committees for the National Academy of Sciences and the EPA. So it's a pleasure to introduce Dr. Webster here to our public health ground rounds. Please take it away, Tom.
All right, thank you very much. I'm very pleased that you invited me. You know, like you said, I am from San Diego, and it's always nice to come back here. All right, so my talk today, first of all, I want to acknowledge my colleague, Mark Weiskopf at Harvard, who is an old friend of mine, and we've done a lot of this work together, so I'll just say a shout out to him first up. And mixtures, yeah, well, I will really be talking today in the context of chemical exposures, which can be pharmaceuticals or environmental chemicals, but you can think about this much more broadly than that. I mean, you could think about social factors, you could think about physical factors like temperature and climate. I mean, there's a lot, but I'm going to do it. I do it sort of in the context of chemicals, because I have kind of a pharmacology background. And I want to explain, first of all, my subtitle, How I Learned to Start Worrying and Love the DAG. And this really is, okay, wait a second, I gotta figure out how to advance the slides here. Here we go. This is really with apologies to Stanley Kubrick, if you've ever seen his film, one of my favorites. And the other thing I want to say very briefly is about the date. So today is actually a very important date. On this day in the year 1600, Giordano Bruno was burned at the stake in Rome. And he was actually an astronomer and mathematician and philosopher. And among other interesting things, he came up with the idea that stars are distant suns with their own planets that may have life, and that the universe is infinite and has no center. And if you're a fan of the Argentinian writer Borges, like I am, you may have read a story called The Library of Babel, where he talks about the universe not having a center. And it's thought that he actually got this idea from reading Bruno. So anyway, a shout out to Giordano Bruno. All right, so when I was a graduate student quite some time ago, I had three things I want to share with you. First was when I took my very first epidemiology class, I thought it was incredibly boring and easy. And it wasn't until later I realized how wrong I was, and thus that it was incredibly interesting and very difficult. The second is that when I took that course, we didn't really talk about causal methods like DAGs, which I'll come back to. It was that long ago. And the third was that I actually thought about doing my dissertation on the health effects of exposures to mixtures. And my advisor, who was actually quite good advice at the time, said not to do it. It was too hard. And I did listen to him, and I did it on something else, but I never quite gave up. And so here I am. All right, so as Jorge mentioned a little bit, I actually am kind of multidisciplinary. I do work in exposure science, environmental epidemiology and methods, and also toxicology. And environmental health is very much like that, very interdisciplinary. And mixtures sort of really involves all three of those. And today, what I'm really going to talk about is primarily epidemiologic methods, not so much statistics, although if you want to ask me, I'd be happy to talk about that. And the other thing that's worth noting is that toxicologists and epidemiologists and statisticians often use the same words, but they mean different things. So when people say interaction or synergy, it means something actually quite different in toxicology and pharmacology than it does in epidemiology. And again, Jorge already mentioned this. I have another big interest in PFAS, but it'll come up. That'll come up just a little teeny bit today. All right. So why is there an increased interest in mixtures in the last few decades? And as Jorge mentioned, we're all exposed to stuff lots of stuff all the time. And this has been known for a long time. The interest in mixtures and pharmacology goes way, way back. Pharmacologists get trained to worry about drug interactions, for example. And so this is not an unknown phenomenon, but it was sort of not paid that much attention to in toxicology and epidemiology. I mean, there was some, but they really received a boost about a decade or so ago. And part of it, there are a couple of reasons. One is NIEHS started investing in this idea. So Linda Birnbaum deserves a lot of credit for that when she was director. And they wrote a series of editorials, and they started having grant money to support mixtures. So that's always helpful. The second is it was increasingly recognized in toxicology how important what mixture effects are and can be. And this was a really interesting paper that was published, quite 20 years ago. And it's called the Something from Nothing paper. And it's a toxicology paper. And what they show here on the left is they took estrogenic compounds in a reporter cell system. They had the concentration of each one individually below its no effect concentration. So you get nothing going on here. But when you mix them all together, you get this gigantic effect. And from a pharmacology, toxicology point of view, we know exactly why this happens. And it's very well predicted by a model called concentration addition. So interestingly, if you come from an epidemiology point of view, this is not, from a toxicology point of view, this is not synergy. This is actually a sort of special form of additivity. So mixture effects can be important. Individual exposures by themselves may not seem to do very much, but together they can have a big effect. So that was the second main thing. And then, and I just to mention, in my toxicology hat, we actually do a lot of work in this. I won't really go into it other than we're very interested in the effects of different chemicals at receptors, and we've worked at a bunch of different receptors. So if you want to ask me about toxicology, we can talk about that. Right, so in the toxicology realm, it's worth keeping in mind different purposes for mixtures toxicology. One is to improve risk assessment, right? So EPA wants to do good risk assessments of mixtures. PFAS and water being a prime example right now. You might want to predict effects, or you might want to understand, like, what is the mechanistic basis for, say, additivity or synergism or something like that. And so this sort of difference of purposes is kind of a sub-theme in my talk today, is that the prediction and mechanism or cause they're not really the same thing. I mean, they're related, but they're really kind of different. And this will be particularly important in the epidemiology context. All right, the third main reason we see a lot of interest in mixtures today is sort of the revolution in exposure, analytical chemistry and exposure science, and in particularly the use of biomonitoring. When I first got involved in this business several decades ago, biomonitoring was really hard. And to measure persistent organic pollutants, people, used breast milk, or they even used adipose tissue samples and all that. And I mean, it has been such a revolution, it's unbelievable. We can now measure many compounds in very small samples of serum or urine for kind of reasonable costs. And it's just going to be more this way with the advent of non-targeted analysis and stuff like that. So this, in my mind, is along with the fact that there's research money available, this has completely changed the landscape. And so one approach to this, which I'm going to talk about in some depth, is you measure a whole bunch of chemicals, right, from a person, and you put them all in a statistical model, maybe with some covariates, and you try to let the software tell you which exposures are important, whether there are mixture effects, which I sort of mentioned, and possibly to construct summary measures of exposure. And there's been a lot of focus on development of statistical techniques. Actually, just a few weeks ago, a program called PRIME that came out of NIHS ended. I was one of the PIs, and we did a lot of work on statistical techniques. So if you want to ask me about statistical techniques, we can talk about that too. So there's a lot of work on that. But my focus today is really going to be on the epidemiologic side, because they're not the same. All right, so the first thing to think about is the difference between predictive models and causal models. So this goes back to what I talked about toxicology. So from a sort of epidemiologic point of view, you can think of predictive models as you take a whole bunch of variables, X's, and you put them into some machine learning, I don't know, whatever your favorite thing is, and you see how well it predicts Y. And you might, in a linear modeling context, you might look at your R square. How well am I predicting Y based on all these variables? From an etiologic epidemiology point of view, on the other hand, we're really interested in effect estimates for exposures and, say, their confidence intervals. So if you're an epidemiologist, this should sound very familiar. And both of these kinds of models really have their purposes. There's a lot of interest in predictive models in the clinical world, identifying populations to target if they have high risk or planned service needs and things like that. And I mean, that's all great. I don't have any problem with that. In a etiologic epidemiologic point of view, we're really interested again in effect estimates, and in particular, the sort of revolution in causal methods in epidemiology tries to think about intervention. So if I were going to reduce exposure to some exposure, will the outcome reduce, right? And so this sort of intervention causal framework has really taken off in epidemiology in the last few decades. So the other thing worth knowing, and there actually seems to be a fair amount of confusion about this, is that to do causal models in epidemiology, you don't usually need fancy statistical methods. Sometimes you do, but a lot of times really what you need is just careful thinking. And that's where the DAGs come in. So I don't know how many of you know much about this, but I'm just going to say a little teeny bit in case no one has. Some people haven't. And it's really sort of a very, very nice way of taking into account causal assumptions. And it consists of variables and arrows. The arrows mean causality and they're directed. They go in one direction and you can't have any loops. So that's why we call them directed acyclic graphs. And so the first one here, this means exposure causes Y. This is a causal effect. And this bottom one, for you epidemiologists, here, some other variable Z is causing both X and Y. And this is what we mean by confounding. Right. And both of those situations are consistent with an association between exposure and outcome. So you can't tell from the statistics alone usually what's really going on here. You have to use some epidemiological thinking to get to the bottom of this, like say adjusting for Z. So how does this come into the mixtures world? So there was a very nice paper by Webster and Greenland some time ago called the Table 2 Problem, which is a very cute title. And here's where it comes from, is that in a typical epidemiology paper, the first table 1 is usually a description of the population, who's in it and various demographics and whatnot. And table 2 has effect estimates and confidence intervals. And so this is just a quote from their paper. But basically what it comes down to is it oftentimes, not always, but oftentimes you might have multiple effect estimates in one table. And for maybe say for different exposures and several confounders based on one model. And the problem is that there's a tendency to interpret all of those as causal, and that can really get you into problems. So let's dig into this a little bit. So an interesting example of this comes from COVID research, and I've sort of oversimplified this example, but you know, it kind of gets the point across. There was an interesting paper that was published a couple years ago in the heat of the moment, you know, when everything's going crazy with COVID, and they were using electronic medical records in the UK from the National Health System. And they're trying to predict COVID-related mortality in hospitals, and they took a whole bunch of variables and put them in a model and see what comes up. And many of these were expected. So heart disease and increased risk, that's not very hard to see. But there was one really interesting unexpected result, which was that smoking in this model had a decreased risk of COVID mortality. And when we all saw this, and we're like, what? That doesn't make any sense. How can that be? And so there's been some work trying to figure this out. And here's one possible explanation for what went wrong in this model, is that if you have smoking can affect heart disease can affect COVID-related mortality. And if you have some uncontrolled social determinants of heart disease and COVID, then what happens if you put both smoking and heart disease in a regression model, is it will actually cause the effect of smoking, given on the arrows here. It'll reverse the sign of the smoking. And if you're an epidemiologist, what's happened is you've conditioned on a collider. Heart disease is a collider here. And this will flip the sign of the association. And that's an artifact of having put multiple things in the model without thinking very clearly about what you're really doing. And so it's from a predictive point of view, this is perfectly reasonable, but from an etiologic point of view, this is problematic because smoking actually is positively associated. So the moral of the story for mixtures epidemiology is that including multiple exposures in the same model can lead to these table 2 problems, i.e. incorrectly interpreting all the results as total causal estimates. And second point that's very important for us environmental epidemiologists is this can be made much more likely when we use exposure biomarkers. Now, remember how I told you exposure biomarkers are really important and we like to use them? All right, so they have good things about them, but they come at a cost, and the cost is we have to think harder. So they're cheaper, and they're oftentimes much cheaper and more accurate measures of exposure because they integrate across multiple routes of exposure, and they include things like behavior and pharmacokinetics. But the problem is that they're more prone to confounding by behavior or physiology. So there's a wonderful example of this that comes from the PFAS literature. And it has to do with the relationship between PFOA, which is one particular kind of PFAS, and birth weight. And typically this has been studied using serum concentrations measured during pregnancy. And this is sort of a cartoon. We get PFOA in serum. It comes from exposure via inhalation, ingestion, maybe dermal exposure. That's a little unclear yet. And there are multiple sources. We can have PFAS in food. We can have PFAS in water. That's the famous one. And there can be PFAS in air and dust in the indoor environment. And all of these contribute to our exposure and hence to PFOA in serum. So it's much, much easier to measure PFOA in serum than to measure these things externally. This would be really hard and very expensive. So we like to do this. So ideally, we would have a situation where the sort of simplified DAG looks like this. We measure PFOA in serum, it's related to birth weight. The problem is this is I think one of the better examples of confounding by physiology, in particular pregnancy physiology, where there are changes in kidney function and increases in plasma volume during pregnancy. And this actually can bias the association between PFOA in serum and birth weight. And there's a really kind of nice paper by Kyle Steenland and company where they looked at this, and they took different studies and they looked at the beta estimate depending on when they took the sample during pregnancy. And the later in pregnancy it got, the bigger and bigger the effect was, consistent with this confounding by physiology. So when I first heard about this, I'm like, oh man, all right, okay, we really need to pay attention to this sort of stuff. All right, so now let's think about mixtures. Rather than one single compound like PFOA, let's think about mixtures and some of how some of these things might happen. And so these are some simple examples using DAGs. So the first one is suppose we have two exposures, X1 and X2, and they're correlated with each other because they have an unmeasured common cause. It might be a similar source or it might be something else, whatever it is. And it's very common in with exposure biomarkers that some things will be correlated and some won't. And as this thing is drawn, both of these exposures cause the outcome, right? Okay, so we've referred to this as confounding by co-exposure, because if you just measured one exposure at a time, did a crude model, it would be confounded by the other one. But if we put both exposures in the model, then we'll get the correct causal estimate. So that's great. That's what we want. All right, and you can imagine more complicated scenarios that maybe the X1 relationship to the outcome is confounded by Z, some variable, SES or physiology or whatever it is. But we measure Z, right? And so if we put X1, X2, and Z in the model, we still get the unbiased causal estimates. So that's great. That's exactly what we want. Right, so that now we can get in, start thinking about some of the, so again, related to that, the same thing happens if we say there's no causal relationship between X2 and Y. So all we've done is just remove that arrow, right? Same thing, we still get perfectly good unbiased estimates when we do the full model. So that's very nice. Now, suppose that Z is unmeasured, like the pregnancy physiology, and we don't really understand it. We don't measure it, so we can't control it. In this situation, right, we've got this unmeasured confounder, and if you here it turns out that if you put X1 and X2 in the model at the same time and try to estimate Y, the estimates are actually more biased. This one gets more biased than it would be than if you put X2 in with it. If you did a crude model, the adjusted model is more biased than it would be than the crude model. And the X2 beta estimate, which should be 0, actually becomes negative, right? So this is actually a situation related to the COVID example I showed you before, right? So that's really a problem, because this kind of thing might happen quite a bit with exposure biomarkers. All right, another class of problems where you can get this is when one biomarker affects another one. So again, in pharmacology, it's quite common for one chemical to affect the pharmacokinetics of another one. Pharmacologists worry about this sort of thing all the time. So here we've drawn a causal arrow between X1 and X2. These sort of situations, I'm actually doing some research on this, but these sort of situations may be somewhat common when large number of environmental chemicals are studied together. So is that they're related to each other through these sort of causal pathways. So in this situation, we can construct a mutually adjusted regression model that estimates the direct effect of X1 and Y on Y and X2 on Y, but not the total effect of Y of X1, because that's also mediated by X2, right? So this is a type of table 2 problem where you can get the direct effects, but you can't get the total effects, which is what you really want. Then there's sort of a even more complicated situation. We'll spend a little bit of time going through this. Then imagine the effect of this exposure on the outcome is mediated by something, and that something affects X2. So as a cartoon example, suppose X1 is PFOA, and there's a fair amount of literature that suggests that PFOA can affect cholesterol levels in serum, in particular increasing levels of LDL. In turn, the levels, what you measure of PBD 47, which is a polybrominated diphenyl ether, it's a lipophilic compound. So its concentration in blood can be related to the amount of lipid in blood, right? And then if you have an outcome that depends on lipid, you can have a situation that looks like this. So X1 is mediated by L on Y, but it also affects L, and L affects X2, right? All right, so if you had this, what happens? And this, again, this is sort of a simple example, but it's not completely crazy either. And what happens is that you cannot write a single linear regression model that will estimate the total effects of both exposure. So L is a mediator of X1, but it's also a confounder of X2, right? Because you've got this backdoor pathway, right? So when you look at X2, you want to adjust for L, but if you adjust for L, you block the effect of X1. On the other hand, if you look at X2, it's a confounder of X1 because there's this backdoor pathway like this. It's a collider because if you adjust for X2 and you go like this, then you've adjusted for a collider, so you've opened that pathway. And it's also a mediator for X1 because you got a pathway like this, right? So turns out there is no single model you can write in a typical regression model that will estimate what you want. So you're kind of in trouble, and you have to use other more complicated methods. So this is an example where more complicated statistical methods like G methods and things like this, you actually sort of have to use. You can't do it the old-fashioned way. Now, Same situation, but imagine that instead of measuring the biomarkers of exposure, X1 and X2, we measure exterior exposure measures, right? So it might be hard, but suppose we could do that. Then mutual adjustment for X1 and X2, X1 prime and X2 prime, the two exposure measures, they actually give you what you want. You get the true total causal effects, right? So that's great. So again, the problem in this situation is that we're using the biomarkers of exposure, but if we go to the external, and that they're causally related to each other, but if we use the external measures of exposure, they're not causally related to each other, so we can then build the model we want. So that's good. All right, so I've mentioned some of the problems you can have. The good news is that you don't always have problems, obviously, and that you can make these things work. So if you have two exposures and you have a confounder for one of them, and you put both of these in the model along with the confounder, you get a perfectly good estimate. Or you might have a situation where you have multiple Z's, one affecting X1, one affecting X2, or maybe it affects the common source. So suppose you have two PFASs that come from the same water supply. So they have a common source that causes their correlation. And the confounder is maybe something like where you live or SES or something like that. And that's the thing that you need to worry about. Well, you can adjust, if you measure it, you can adjust for it. And then again, you can be in a situation where you can get the causal estimates that you want. And so in these two situations, what makes it work is that there aren't any causal connections between the exposures, right? There's no error, there's no pathways between X1 and X2. And the confounders are measured and adjusted for, right? So when you have those sorts of situations, then the approach of taking all your exposures and your covariates and putting them in a statistical model, in principle, should give you the right estimate. Okay, so sort of in conclusion here, you know, in environmental epidemiology, we generally want causal models, not predictive models, I think. I mean, it's not always true, but that's what I want. And I think that we sort of need to resist the temptation to simply put multiple exposures and other variables in a model, some statistical model, because that can lead to table 2 problems. And I think the way around that, the sort of the secret sauce, is to use causal reasoning like DAGs or some other approach to identify what we should and should not adjust for in any specific analysis. That sometimes no regular simple regression model will do the job, and you have to use sort of fancier methods. And that, you know, I mean, I'm a great believer in the use of biomarkers of exposure because they can make a lot of this work possible, because you can actually measure things for finite amounts of money. But it comes at the cost of that we have to think harder. We have to think about confounding by physiology or sometimes behavior. And that it's sometimes useful to think about external exposures when you do the modeling, to think about what would happen if you had an external measure of exposure, and that can be very helpful. So another example with the PFOA that I've been working on is when you have, there's some concern, say, with the effect of PFOA on serum lipids, that there can be another form of confounding by physiology having to do with bile acid transporters and things like that. That if you use a serum biomarker, you can have this kind of confounding. But if you have an external measure of exposure, you don't. It actually acts like an instrumental variable. So you can sometimes, if you have both, you can try to dissect how much of it is actually coming from potentially from confounding by physiology. So it's very useful to think about it that way. So let me just finish up here by some acknowledgements. Like I said, we just finished this NIH Prime program, gosh, what, a month ago? And that was a huge help supporting my work on mixtures in epidemiology and causal reasoning. I have another NIH grant on toxicology, and I want to thank particularly Mark Weiskopf. And then I want to mention something. I don't think any of you know this. I should have put this in my bio, but I was actually a student at UCSD for a while back in the old days. And I worked with Kent Wilson. I don't know if any of you ever heard of him. He was a professor of chemistry who died tragically young of cancer. And I worked with him on my very first peer-reviewed paper, which was looking at air pollution and SES in Los Angeles, sort of a very early form of environmental justice research back in the old days. And there I am. There's my name, and there's Kent Wilson. So he was a wonderful mentor of mine. And anyway, so I have kind of fond feelings for UCSD. All right, so that's all. Thank you very much. I know I finished a little early, maybe 5 minutes, but we have lots of time for discussion.
Thanks so much for the presentation. A lot of food for thought in general when we're talking about analysis, and you're absolutely right. This is the example from the environmental health chemical world, but it really applies to just about anything social epidemiology.
Absolutely.
All sorts of different constructs, which starts getting very complex. So we'll start. Please let us know if you have any questions. Please raise your hand and we can include you. I see we have a question here from it's a phone call apparently, so I can't see who that's from. And then Loki. So there's a phone number.
They're muted.
Somebody who's calling in apparently is muted, but there we go.
Okay, can you hear me now? Thanks.
Yes.
Hi, I'm Beatrice Galam, professor in the Department of Medicine. Lovely talk. We're very interested in chemical mixtures because our lab has a focus on a condition called Gulf War illness, which involves multiple drugs and chemicals to which service persons were exposed in the 1991 Gulf War. I just want to comment on the issue of the smoking with the COVID research to suggest that there are multiple potential explanations for that. Two other ones that I might suggest are that smoking does in fact activate the alpha-7 nicotinic receptor, which is known to have multiple neuroprotective and other effects. So there's sort of a strong bias to assume that smoking is always negative. And the reality is, I suspect in this case it probably is, but the other thing that I would suggest is that smokers may come to medical attention earlier with their COVID with less severe underlying COVID, so that they may end up having less adverse outcomes because the smoking itself contributes to a type of symptoms that are not tied to the most severe adverse COVID outcomes. So just among the other potential explanations for that finding.
Yeah, I quite agree. I mean, I gave a very oversimplified example of one possible way, but I think it's interesting that often we end up in this situation where there are multiple explanations, including causal and non-causal ones for results we get. So,
great.
Thanks.
Anyway, thanks again so much for an excellent presentation.
Can I go, Jose?
Oh, yes. Sorry, I was muted. Please, Loki, take me just for the question.
Thank you for a great talk. This was fantastic. I'm a statistician and I'm sort of learning DAGs as I go. And we actually had a presentation. We have a journal club and we discussed DAGs in our last journal club. And I wish I had known your paper because this would have been a perfect example for next time. However, I do have a question. So I thought your slide, I think it was 2 before, where you outlined when it's okay to have multiple exposures in your same model. You had these examples and these examples. Is that, are those, it sounds like you're saying those are sufficient. Are those necessary? So I guess my question is it possible to write down this, if these things are satisfied, go ahead and use your regression model?
Yeah, that's a really good question. I actually put this slide together this morning because I was like, oh man, I left people with such a bad impression, like you should never do this because it'll never work. And I thought, well, here's some cases where it will work. And so I have not actually tried to, I'm actually writing a paper about this, trying to figure out when is it necessary and sufficient. So it's an excellent question. In these particular cases, if these are the assumptions, it will work. but there are other ones. There are other ones, and there are probably exceptions to this too. I don't know. I have to sort of think that through.
Thank you. It's a complex question,
Yeah.
field.
But I think that's the whole point, is that particularly in the era of big data and machine learning, there's really this tendency of putting everything in a model. And from my point of view, if you want to build a predictive model, that's great, actually. But if you're trying to understand mechanism, you have to be really, really careful. And it's interesting that I'm part statistician too. We don't seem to talk about this in statistics, and it's I don't know. I mean, epidemiologists are obsessed with cause, right? And so it's sort of an interesting disjunction between the two fields.
I agree, and yeah, we're trying to change that, I think.
Yay!
Thank you, Lucky. I had a question too. Actually, I have two different questions, Tom. So kind of going back to your slide about PFAS and then PBDEs, I think it's a couple of slides back on that. And just to give a little background for those of you who are not familiar with PBDEs, so these are flame retardants. And actually, it's very close to, I guess, California's exposure history back in the 2000s to until now, where concentrations in humans, even in breast milk of California women, were substantially higher than anywhere else in the world. And it's because of the introduction of TB 117 by here the state of California, which then resulted in the introduction of all of these flame retardants into upholstery, just about anything that had foam in your house. So sofas, chairs, anything, until then, they started getting phased out in 2015. In any case, so as you mentioned there, those PBDEs are fat soluble, lipophilic, and you brought in the example of how PFAS with that X1 would then result in alterations in lipids. And because PBDE tends to be bound to lipids, then of course the concentrations, in this case, let's imagine it's serum, would then affect that exposure biomarker, or the concentration of the PBDE, right? So this is kind of a problem there, as you had discussed. Now, a lot of people tend to simplify variables a little bit, in which they say, all right, we have PBDE, let's divide that by a lipid content. So then you have this X2, which is actually a ratio of the concentration of the PBDE divided by the lipid, which then you could say, well, maybe that helps us bypass the situation. What are your comments in that?
Yeah, no, it's a really good comment. I mean, there's been this sort of argument in the literature of what's the best way to deal with lipophilic compounds. Should you standardize it sort of by the amount of lipid, or should you adjust for lipid, or should you not adjust it at all? And what was it? Schusterman, I think.
Schusterman, that's right.
I wrote a couple nice papers about this. I haven't really tried to do this. I don't know how to do the mathematics for that, to figure that out. I would probably just do a simulation. It's a good question, though. It might be that if you lipid standardize, it might break the arrow. I don't know. I don't know. It's a good question.
I guess and my second question, which is maybe a little more ethereal in some ways, is we're talking about mixture models, right? It could just blow our minds. We can measure 5,000 different chemicals and then think, well, let's analyze the interactions between them, which would then result in thousands of interactions, the whole mixture modeling component. We now have better, more advanced tools to do this, including machine learning, like, Bayesian kernel machine learning regression, or weighted quantile sum regression, et cetera, et cetera. To what point can we rely on these, even if we have given a lot of thought to what will be potential colliders, et cetera, within that? To what extent do you see this really helping us kind of at an automatic way to start getting around some of these concepts, other than just the ability to be able to better characterize mixtures of exposures and how they may be related to the outcome? Hopefully
Yeah. No, I mean, I've thought about this a lot. Again, that's why I tried to try to put this in, like, when will I think this would work? And then you'd still have to worry about things like collinearity and stuff like that. But at least the model isn't going to give you bizarro results. And so I think there are cases where it will work okay. I do really worry. I think that the thing that really worries me is about effects of some compounds on the concentrations of others. Whether it's through, it might not be the lipid effect. I mean, I just used that example because it was sort of, I used to work on PBDs and I work on PFAS. So, but if one common compound affects the pharmacokinetics in another way, like it induces some enzyme which turns on, phase 1 or phase 2, and then it changes. I mean, again, pharmacologists think about this all the time, and I don't know how important it's going to be for environmental chemicals because we're at sort of lower doses, In pharmacology, you're at high doses, so you really, really have to worry about this. In environmental chemicals, I don't know, but it worries me a lot. Now, on the other hand, the good news is I've done a lot of work looking at sort of correlation diagrams. So you take a whole bunch of chemicals and you look at the correlation of everything with everything else, and then you plot it out. And it turns out that a lot of times things are not correlated. And sometimes they are, and sometimes they're not. And so you get these sort of block diagonal things. And so some groups of compounds will be very highly correlated. The PBDs tend to be correlated with each other. The PFAS tend to be correlated with each other. But in general, like again, I sort of cheated here. PBDs and PFAS, this U that I drew in here, I was pointing with my finger, that's not very helpful. This U, they're very low correlations between PFAS. Say PFOA and PBDE. So maybe this L thing isn't really that important, or I don't know. This isn't here, and maybe it's because they're not related by SCS, or maybe there's something else going on. So it may not be quite as bad, and that we can think about it partly that way too. Like, how can we use our knowledge about how the exposure happens, which is a lot easier. It's a lot easier than the biology, right? And that may help us be more at ease with what we're doing.
Mm-hmm. Mm-hmm.
So I'm reasonably hopeful, but I do think it really requires a fair amount of thought, So.
Rainey has a question. Unfortunately, we can't hear you. You're unmuted, but it looks like your microphone is not working, maybe. Yeah, still not picking up your audio, Rainey. So so he's going to type his question. So while this happens, Tom, another question for you in that regard. So mixture modeling is now in vogue in the field of environmental health. You can't get a grant funded if you don't describe that as part of your methods section writing, even publishing papers in which you've been measuring a lot of different chemicals. It's getting harder to get away of not having these types of analyses in that. So is this something that that you foresee maybe applying to all fields within epidemiology and public health, for that matter, given just the complexity of the interactions that we're not really looking at smoking and the heart disease necessarily, but there's a whole milieu of different behaviors and other co-exposures. Thoughts on that?
Yeah, I don't know, but it's certainly true that there are connections between traditional environmental health problems, nutrition, pharmaceutical use, and then social factors. And we've sort of known this for a long time, the intersection between social factors and environmental health. So I would think that if we want to do this right, we're really going to have to start applying this sort of mixtures lens from this much larger point of view. I think that's true. That, is like a really big challenge, but, it's a real opportunity. And I think we've got some of the tools to do that. So.
Yeah, I mean, and since Loki is here too, I mean, it's something that just to put in the radar too for preparing our students in that direction, given the complexity of what this whole talk has been about. It's been very simplified, but it's actually very, very profound to what we're doing, and then providing our students with a lot of the different tools to be able to get to this. I see a couple of questions here. One from Wael. He's asking about your thoughts about structural equation models versus linear regression models for exploring the DAG. What are your thoughts on that?
Oh, yeah, I actually tend not to use structural equation models. I don't really know why. I mean, in the mixtures world, I've done a lot of work with things like Bayesian kernel machine regression, and then a spin-off of that we've been working on called a Bayesian multiple index model, where you can it's sort of a long discussion, but I've tended to go more that way. But yeah, I think structural equation models, I mean, they have pretty strong assumptions too. I like to use linear models and examples just because you can kind of figure out the mathematics pretty easily. When things become nonlinear, then it obviously becomes a lot harder. So I don't know. That's not a very satisfying answer, other than, yeah, I think structural equation models, sure, that can help us. Other than, in general, I think that we have to assume DAGs. We can't actually infer them from the data, except in maybe there's some very special circumstances that you could, in other words, there can be multiple DAGs that are consistent with the same data, and there's no statistical way to tell them apart. And so we just have to use expert knowledge and kind of our best guess at what's going on, and then talk about the strengths and limitations of that.
Fantastic. A question for Rainey. He says one of the major challenges with DAG is having knowledge of the relationship between the markers and the potential confounders or mediators.
Yeah.
So why not go back to predictive models, at least in scenarios in which knowledge is limited, as a starting point?
Oh, yeah. So again, I think predictive models, I mean, I should have been more clear about this. Besides being really useful for actually prediction, which often we want to do, is they can raise nice hypotheses, and then we have to try to test them more rigorously. So I don't have any problem with that, because you're right. The DAG is really a set of assumptions, and if we actually knew the DAG were true, then we wouldn't have to do this study except to measure things, right? So what I tell my students is, well, come up with the best DAG you can, and maybe some alternatives that are plausible, and then we have to sort of think through what they all mean. So this is one of the reasons, like, epidemiology kind of looks easy, but it's actually really hard, because a lot of times we don't actually know. That's what makes biology complicated, is we don't actually know what those structures look like under the hood.
Thank you. And we have time for a final question. Well, if no additional questions, I would like to thank Dr. Webster. Thank you very much for an excellent talk, and we enjoyed having you here, and hopefully we can catch up while you're in town.
Yeah, it'd be nice to meet up in person sometime. All right. Thank you very much for having me. I appreciate it.
Great.
Great talk. Thank you.
Thank you.